This is Dr. Sridhar, back to you with another video session on Norton's Theorem. So in my previous videos, we have discussed about various network theorems and problems also. In today's video session, I am going to elaborate this Norton's Theorem with the help of one basic problem. So how this Norton's Theorem can be implied to find out the currents through one or two elements, and in what way this Norton's Theorem is useful for us to simplify the electrical circuit. So let me take one simple example. Having one voltage source 20 volts and 4 resistors. One is 4 ohm resistor and 2 ohm, 5 ohm and 3 ohm resistor. Let me collect what we have studied in our previous video sessions. What is the definition of Norton's Theorem and how we are going to determine the equivalent of Thevenin's equivalent resistance and IN current. Just for a recap, let us elaborate what is the statement of this Norton's Theorem. This states that any linear bilateral network containing several voltages, currents and resistances can be replaced by just one single current source in parallel with a single resistance, and these two must be connected across the load. Now this is the statement. This statement just helpful for us to recollect what we have learnt in our previous sessions. This short circuiting current or Norton's current we are going to represent as the equivalent of the current source in the Norton's theorem, that is IN or ISC, and this RN is nothing but just more or less similar to our RTH. This is the method, the same method how we are going to calculate the Thevenin's equivalent resistance. This RTH and RN are both are same. And coming to the how we are going to determine the equivalent resistance, that is RTH or RN means voltage sources we are going to short circuit and current sources we are going to open circuit. So finally, any electrical circuit, any electrical network represented like this can be reduced, can be converted into this particular form. This is nothing but Norton's theorem. So here, if you could clearly observe, this is nothing but the IN is nothing but Norton's equivalent current, and this RN or this is also called as a RTH, and this is the load resistance. It means through which element we are interested to find out the currents. So this is just a recap for this Norton's theorem, and let us make use of this basic idea of this Norton's theorem to calculate the current flowing through 3 ohm resistor. So whatever the current through this particular 3 ohm resistor, that we are going to discuss in today's video session. For RN, just now also we have discussed, we are going to short circuit the voltage sources, means short circuiting in the sense equivalent internal resistance of voltage sources and current sources, right? And next one is we are going to make load resistance. That load resistance already we have discussed so many times. The element through which you are going to determine the current, that resistance you have to treat as a load resistance. So that load resistance and terminals are nothing but the load terminals. This is point A and this is nothing but point B. At the same instant, short circuit the voltage sources. Now this is simply we have short circuited the voltage sources also. So the remaining network we have not disturbed anything. The 4 ohm resistance as it is there. 2 ohm resistance is there. 5 ohm resistance is there. Only two modifications we have done here. That is short circuiting the voltage source by keeping the internal resistance of the voltage source with this red color, that is short circuited, and load resistance also we have determined. I mean to say we have earmarked some load resistance, that is nothing but the 3 ohm. Now if you could see here, this 4 ohm resistance and 5 ohm resistance, these two are exactly parallel to each other. So 4 ohm and 5 ohm is parallel to each other. Then the equivalent of this is nothing but 4 5 ja plus 4 plus 5, that is nothing but the 20 by 9. So 2.22 ohm resistance you can see between these two terminals. This is the same thing we are going to right here. This is 2.22 ohm and this is nothing but the 2 ohm resistance. So this is a way of doing the calculations for determine RN value. So Rn is nothing but just 4.22 because 2.22 plus 2 ohm is nothing but 4.22 ohm. So just go back to IN value and ISC value. This is very important here. So in order to calculate this short circuiting current or Norton's equivalent current, now you have to short circuit the load terminals. Now see, just now what is the load here? Load is nothing but this is the our interested. So actually our intention is what is the current through this 3 ohm resistor. So it means this value is nothing but our load resistance. So as per our statement, so we have to short circuit the load terminal. So remove the load and just short circuit the load terminals. Then with respect to this, you have to determine whatever the IN value or ISC values. So this current is nothing but the Norton current. So once if it is short circuited the load, how much of current it is flowing? So that is nothing but the Norton current. That Norton current you have to determine here. So how can we do that? So this is nothing but a simple loop, and this is another loop. So by applying KVLs or KCLs, those are nothing but the fundamental laws available in the electrical engineering. With the help of that fundamental laws, we are going to determine IN value. See, in the first loop, the 20 volts voltage source is supplying the energy to 4 ohm resistor, and this 5 ohm resistor is shared by the two loops. Now see, if you are applying the KVL, then what happens? 4 ohm, this is across this 4 ohm, what happens? Let the current is, if it is assumed as I1, so 4 into I1, and across this 5 ohm, what happens? So 5 into I1 minus IN current. So this is 4I1 plus 5I1 minus IN. So 4I1 plus 5I1. So that is nothing but the 9I1 minus 5 into IN. So minus 5 into IN is nothing but the 20. So like this KVL of this first loop can be marked, and similarly KVL for the second loop also. Because across this 5 ohm, that is the drop is nothing but IN minus I1 into 5 ohm. So the drop across this is this, and this is nothing but the 2 into IN. So whatever the voltage source, any active voltage sources in the second loop, there are no active voltage sources. So this value is minus 5 into I1. So minus 5 into I1. Yes, minus 5 into I1, it is clearly written here, plus IN into 5. So 5 IN plus 2 into IN. So totally 7 IN is equal to 0. So minus 5 IN, minus 5 into I1 plus 7 into IN is equal to 0. So this is the KVL of the second loop. Only the thing is, here by knowing these two equations, loop equations, let us simplify and let us find out whatever the I1 current and IN current. So I1 current is 3.68 and IN current is nothing but the 2.631 amps. So like this, we are going to determine whatever the IN current. So already in the previous slide, we have calculated whatever the Norton's equivalent resistance or Thevenin's equivalent resistance. And in this current topic, in this current slide, we have determined whatever the IN value, that is 2.631 amps. So after getting this Thevenin's or Norton's equivalent resistance and Norton's equivalent current source, just you represent these parameters, these values in the equivalent circuit. So equivalent circuit is, this is the IN current and this is the RN. So 4.22 ohm and this is 2.631 amp. So this is nothing but the load. So what is our interest now? So whatever the current here, this current is nothing but let it be I1, whatever the value of this particular I1. So how can we find out this? So here, let us assume this is IN current, which is nothing but the IT current. So as per our current division principle, current in any parallel path, suppose if you are taking a circuit like this. So this is R1 and this is R2. So this is R1 value, let this is R2 value. This current is I2 current, this current is I1 current, this current is IT current, total current. So as per our current division principle, so whatever the I1 current is nothing but the total current into opposite side resistance, that is R2 by R1 plus R2. So similarly, I2 current is total current into the I2 current is flowing through which resistor? R2. So opposite of this R2 is nothing but R1 divided by R1 plus R2. So just simply make use of these two simple principles and you apply here. So whatever the current through this RL is nothing but, so I1 is equal to, total current is 2.631 into opposite side resistance, this is nothing but Rn only, that is 4.22 divided by 4.22 plus 3 ohm. This is like this, we are going to achieve I1 current. Just as it is, now we have also earmarked here. Just to simplify this value, we are going to get whatever the I3 value, that is 1.53 amps of current. So like this is the method used to determine the currents and voltages across the various elements. So we have reduced this given circuit into this particular form, and Rn value we have calculated, In value also we have calculated. So finally we have replaced or converted this given electrical circuit into a Norton equivalent circuit, and finally we have calculated the current through RL, that is nothing but the 3 ohm resistance, that is 1.538 amps. Now this is the one of the important problem. In our previous videos also, the same problem we have taken, and there also we have calculated the currents by using Thevenin's principle. Here we have verified that value with the Norton's theorem. Hopefully this problem helpful for us to understand the basic concepts of Thevenin's theorems and Norton's theorem. Thank you. Thank you very much for watching this video. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.